Today we are going to learn the topics of artificial intelligence, which is very important, that is robotics. In that robotics, we are going to see the path planning for pointer robot. Myself, Dr. Bhagwan.Hanchate from Vidya Pratishthan's Kamal Nayan Bajaj Institute of Engineering and Technology, Baramati, India. Let us see now suppose I got we have got the set of obstacles as shown in the environment, as shown in the figure. So we have got the obstacles and we restrict the motion of the robot to a large boundary or bounding box that contains a set of polygons. In other words, we add an extra infinitely large obstacle, which is the area outside the B. So we have got the set of obstacle which is shown in the figure, and as being the environment where we restrict the motion of the robot, and the robot will move in the area of the box B, and we add an extra infinitely large obstacle which is outside the B. Now you can see now the algorithms for the path finding. So first step will be to compute the trapezoidal map of the free space. This you can see in the figure. So we have got a trapezoidal map, and that map you can see now in the to the left hand side. We have got the three figures, and in the three figures we have got the one of the figures is a pentagonal figure, and then we have got a triangles. And again we'll convert this into the right hand side, and this is called as the boundaries of the obstacles. This step takes the big O notation n log n time, where n is the number of segments which are being there. This time complexity is due to the sorting the vertices by x coordinate before constructing the trapezoidal map. So we have got the this is the first step, that is we are going to compute the trapezoidal map in the free space. Next is the construct the road map from the trapezoidal map. Now we have got a trapezoidal map is there, and then we have got a area which is being opened area, and we take the center of each trapezoidal and join it with the midpoint of its two neighboring vertical extensions as follows. We can see it in the figure. What we have done is that we take the center of each trapezoidal, and after taking the each center of the trapezoidal, we joint it the midpoint of its two neighboring vertical extensions. So we have taken the midpoint and then we join it. This road map can be constructed in a omega, that is oblique notation and time, by traversing the doubly connected edge list of the trapezoidal map. Next is the step 3. So we are going to see that use the breadth first search to compute the path from the starting point to the destination. The road map has one node per trapezoid. The node per vertical extension. The road map has a one node per trapezoid and node per vertical extension. Both the number of trapezoids and the number of vertical extensions are linear in the total number of vertices of the obstacles. That is going to be the obstacles, that is we are going to add these two things, that is both the number of trapezoids and the number of vertical extensions. Therefore the breadth first takes itself big O(n) time. So finding the trapezoids containing the starting point and the destination takes a big O(n) by linear search. Therefore, the overall algorithm takes big O and log n time. So the obvious observation is that this algorithm does not find the shortest path from the starting point to the destination. An algorithm which will find the shortest path with the cost of greater time complexity will be presented later on. So let us first revisit the problem of polygon robot versus a pointer robot. So see now, as described earlier, there are certain forbidden points in the workspace which the reference point R of a robot cannot traverse. It cannot trespass. Otherwise, the robot will intersect with the obstacles. This is illustrated in the figure. So robot is moving from one point to another point, and there are certain forbidden points are there in our area, in our workspace, with respect to the point R, our robot, and cannot trespass. Otherwise, the robot will go into the obstacles and it will collide with the obstacle. So we can reduce the problem of motion planning for a polygonal robot to that of a point robot by enlarging the obstacle to all these forbidden points, these forbidden points are there, which are being called as obstacles points. The boundary of these forbidden points can be obtained by tracing out what happens to R when the disk is moved around boundary of that obstacle. Alternatively, this forbidden area can be computed by a mathematical tool called the Minkowski sums, which we'll see in the next section. How you do the Minkowski sums to find the path of our polygonal robot. We can just compute the path for point robot in resulting set of large obstacles.